Hello friends, this is a small problem on strength of materials. So in this problem we have got an aluminum shaft. It is a stabbed aluminum shaft in which the diameter, by the way, it's a circular cross-section shaft. The diameter changes at this junction B from 20 mm to 30 mm, and throughout the material is aluminum. There is no difference in materials in these two sections, and the Young's modulus is 69 gigapascal. And the dimensions are given. The lengths of the portion AB and BC are 300 mm and 250 mm respectively. And we've got these external forces. At section C, this 20 kilonewton is applied in the positive x direction, and at section B there is an external force of 12 kilonewton is applied in the negative x direction. Now in this problem we need to calculate what are the stresses produced in the portion AB and BC, and which is the maximum stress, and what is the net change in length due to these external forces. And the net change in length could be negative, it could be positive. We'll be figuring it out as we go along the problem. Now the first thing we should be doing is drawing the free body diagram for this numerical problem. So let me choose the black color again. Yeah. Now the idea of drawing the free body diagram is we should be replacing all the supports with the equivalent forces, reaction forces, which will keep the system in equilibrium. So this is a kind of a cantilever kind of a beam having a built-in support at section A. So we remove the support and replace the support by this reaction RA in the horizontal direction. So we can appreciate this thing, the external forces which are applied are all in horizontal directions. So the reaction which is produced at A is going to be in the horizontal direction. There is no vertical reaction produced, although this support is capable of giving vertical reaction and reaction moments, but there is no action of these two, neither in vertical direction nor there is a moment produced. So the only reaction that we'll be getting is a horizontal reaction at A, and we assume the direction is positive x direction. Now there is at A RA, and at section B there is 12 kilonewton force, and at section C there is 20 kilonewton force in the positive x direction. Now once we have the free body diagram of the overall shaft ABC, let's cut the shaft into two portions, individual sections, and individually drawing the free body diagram of these two portions AB. Now first we have got a reaction. Now before we do that, we should first be calculating our reaction force. Just excuse me for this. Now for calculating the reaction force, we will be using the equation for the static equilibrium, which is the summation of all the forces in x direction should be 0. Now we have got RA positive, negative 12 kilonewtons, and positive 20 kilonewtons. The summation of all these forces should give you 0. So it turns out that reaction at A is negative 8 kilonewton. Now what does this negative sign signifies? It just means that our assumption on the direction of RA is wrong. The sense of RA is going to be in the negative x direction, 8 kilonewtons. Now we have got RA as 8 kilonewton. So let's draw the free body diagram of these individual sections AB and BC. Let us see what forces are these are experiencing. So RA of 8 kilonewton. So keep this portion AB in equilibrium, we have to apply what? An equal and opposite force at B, which is nothing but 8 kilonewton again in the positive x direction. Now what about section BC? Now at section B we are having 12 kilonewton externally applied load, and as the equilibrium of AB says, at B there is a 8 kilonewton if we consider the equilibrium of the section AB alone. The net result at B should be 12 kilonewtons in the negative x. So how much we should be applying at section for the equilibrium of section BC? 20 kilonewtons. So the net result is going to be 20 minus 8, it is 12 kilonewtons in the negative x direction. And at the free end C we are already having 20 kilonewtons. So it turns out that if our calculation is going right, we should be getting the same load as which is applied at section C. So the portion AB is under tension, so as the portion BC. Both are experiencing tensile forces. So overall there is going to be increase in the system, increase of length in the overall shaft. And you can appreciate at this point that there could be scenarios in which the individual section may undergoing compression and tension, which may mutually nullify and result into no change in the length of the system. But in this case we will be experiencing overall increase in the length. Now the first part of the problem is to calculate the stresses produced in the section AB and BC. So the job will become pretty simple now onwards. The stress in portion AB is nothing but load upon area for the portion AB. So it's going to be 8 kilonewton divided by pi by 4 into d is 20 square, area is cross section mm square. So it will give you, I'll use my cheat sheet to write the answer, 25.5 Newton per mm square. And this is nothing but 25.5 megapascals. Similarly for the section BC, we are having the load the section BC is experiencing. Stress produced in section BC is going to be load upon area section BC, and when you plug and check these numbers with lack of space, I'm just writing it here, it's going to be 28.3 megapascals. So the crux of the problem was to know how much load these individual sections are experiencing by drawing the free body diagrams and applying the equilibrium equations. So load upon area gives you the stress values in both the sections. So the maximum stress produced is in the section BC, which is 28.3 megapascals. Alright, now the second part of the problem is to find out the change in length of these two portions. Both are undergoing the increase in length. So the overall change in length is change in length in the portion AB plus change in length in the portion BC. Both are positive. So with our popular formula, net extension is nothing but PL by AE, and it will just come from our Hooke's law formula. Stress upon strain is Young's modulus. So strain is sigma by E. So change in length over original length, load upon area, stress is load upon area by E. So change in length is nothing but PL by AE. So you all must be knowing, just a quick revision on this. So we'll just plug and check this formula, in this formula the values, and we'll get the numerical values. So PL by AE for the portion AB and PL by AE for the portion BC, and we have got all the numerical values for these individual terms: load, area of cross section, the length of the individual sections, and the Young's modulus. We just plug and check and it will give us the right numerical values. So load in the section AB is 8 kilonewtons and length is, the length of the portion is 300 mm for portion AB, and 250 mm for the portion BC. Just put these values. 300 mm, area of cross section is pi by 4, diameter is 20 mm. I just forgetting this. It's going to be square, and 69 gigapascal. I just rub this portion up. And the numerical values for this section BC is, again, load experience is 20 kilonewtons, length of the portion is 250 mm, area of cross section is pi by 4 into 30 square, so mm square, then 69 gigapascals. Be consistent with the units, plug and chug. The numerical values of the individual terms will turns out to be 0.1107 mm for portion AB and 0.1025 mm for portion BC, and the result will give you 0.213 mm. So this is a net extension in the overall system, 0.213 mm, and the units, you have to be consistent with the units, and I will advise you to go along with Newton per mm square. Put dimensions and area of cross section in units of mm, and forces in kilonewtons, newtons. That's okay, but dimension, if you consistently go with mm squares, so you will end up with newtons per mm square is megapascal. So that will give you a little more ease in calculation. So these are the results, and I hope this tutorial is helpful, and we'll be doing more numericals in the time to come. Thanks for watching. Thanks.